Take a block of steel. Drop it from a height. Watch it hit the ground. Now take a diamond. Same test. The diamond shatters. The steel bends. So which one is stronger? The answer depends on what you mean by strength. Are we talking about hardness, the resistance to scratching and deformation? Are we talking about tensile strength, how much you can pull on something before it snaps? Or are we talking about toughness, the ability to absorb energy without breaking? These are all different properties, and different materials excel at different things. But for the purposes of this journey, we're going to focus on a more fundamental question. What material can withstand the most extreme conditions before its atomic structure simply gives up? What substance can resist forces that would vaporize everything else? What is the strongest material in the universe? Your first instinct might be to think of diamonds. They're the hardest naturally occurring substance on Earth, formed deep in the mantle under immense pressure over billions of years. Each carbon atom bonds to 4 neighbors in a rigid tetrahedral lattice, creating a structure so resistant to deformation that we use it to cut through almost anything else. Then maybe you've heard of graphene, a single layer of carbon atoms arranged in a hexagonal lattice. In theory, graphene is about 200 times stronger than steel while being incredibly light. Scientists have calculated that a sheet of graphene, the thickness of plastic wrap, could support the weight of an elephant balanced on a pencil. The problem is, we can't make perfect graphene. Every imperfection, every missing atom, every slight irregularity creates a weak point. The theoretical strength remains mostly theoretical. What about carbon nanotubes? These are essentially rolled-up sheets of graphene, and they have similar problems. In laboratory conditions with perfect alignment and no defects, they're extraordinarily strong. But scale that up to something you could actually use, and the strength plummets. The real world is messy. Or maybe you're thinking of some modern superalloy, something engineered at the molecular level for maximum performance. Titanium alloys used in jet engines, tungsten carbide in drill bits, steel infused with carbon, and chromium and vanadium. We've gotten very good at making strong materials. But here's the thing. None of these even come close to what exists out there in space. Not even remotely close. We're talking about materials so strong that if you tried to express their strength relative to steel, you'd be counting zeros until you got bored. We're talking about matter under such extreme conditions that the rules of chemistry stop applying, and we have to start thinking about nuclear physics instead. We're talking about substances that make diamond look about as sturdy as wet tissue paper. So forget everything you know about material science. Forget engineering and metallurgy. We're going on a journey from the familiar materials of Earth to the most extreme matter in the universe. And by the end, you'll understand why the strongest material that exists is something you definitely don't want to touch. Let's start with what we know. Here on Earth, material strength comes down to chemistry. Specifically, it comes down to how atoms bond to each other. Take diamond again. Carbon has 4 electrons in its outer shell, and it wants 8 for stability. So each carbon atom shares electrons with 4 neighbors, creating 4 covalent bonds arranged in that tetrahedral structure. These bonds are short and strong, and the geometry means forces get distributed evenly through the lattice. That's why diamond is so hard. You can't push atoms past each other easily because they're locked in place by multiple strong bonds pulling in different directions. Now, compare that to graphite, which is also pure carbon but arranged differently. In graphite, each carbon atom bonds strongly to 3 neighbors in flat sheets, but the sheets only connect to each other through weak van der Waals forces. That's why graphite is soft and slippery. The sheets slide past each other easily. Same element, radically different properties, all because of structure. Graphene takes this further by isolating a single sheet. Now you have a two-dimensional material where every atom is bonded to its neighbors in the same plane with no weak layers to slip. The carbon-carbon bonds in graphene are among the strongest chemical bonds that exist, and they're all pulling in the same flat plane. If you could make a perfect sheet and pull on it, you'd need to apply about 130 gigapascals of stress before it would tear. For reference, steel typically fails at less than 1 gigapascal. But again, perfect graphene doesn't really exist outside laboratories, and even there, only in tiny patches. Any real sample has defects, and those defects are where it fails. A crack propagates from a flaw. A missing atom becomes a tear. The theoretical strength is impressive, but the practical strength is limited by imperfection. Steel and titanium and tungsten are different. They're metals, which means their atoms don't form discrete bonds like carbon does. Instead, metal atoms release some of their electrons into a shared sea, and the positive ions sit in a lattice held together by their mutual attraction to that electron cloud. This makes metals more flexible than ceramics. The atoms can slide past each other more easily, which is why you can bend steel, but you can't bend diamond. But it also means metals are ultimately weaker. The metallic bond is less directional and more forgiving than a covalent bond. Modern metallurgy tries to get around this by creating alloys, mixing different elements to disrupt the crystal structure in useful ways. Add carbon to iron, and you get steel. Add chromium, and you get stainless steel. Add nickel and molybdenum, and you get superalloys that can withstand the temperatures inside a jet engine. But you're still working with the same fundamental constraints. You're still playing with chemistry. You're still limited by the electromagnetic force holding atoms together. And there's only so strong that force can be. The theoretical maximum strength for any chemical bond is somewhere around 100 gigapascals. That's the limit of what chemistry can do. You can't make atomic bonds stronger than the electromagnetic force allows, and you can't pack atoms more tightly than their electron clouds permit. At a certain point, you hit a wall. Earth's gravity and environmental conditions also prevent stronger materials from forming naturally. Diamond forms at high pressures, but nowhere near the pressures needed to create truly exotic forms of matter. The deepest point in Earth's mantle reaches about 140 gigapascals and temperatures of a few thousand degrees. That's enough to create diamonds, but it's nothing compared to what happens in space. So we need to leave Earth. We need to go to places where pressure and temperature reach extremes our planet can't match. Places where gravity is so intense that matter gets crushed into configurations that simply don't exist here. Our first stop is the interior of giant planets. Jupiter and Saturn aren't just big balls of gas. They're big balls of gas with something very strange in the middle. As you descend into Jupiter, the pressure increases. At first, you're in an atmosphere of hydrogen and helium, same as the outer layers. But keep going deeper, and the pressure gets so intense that something remarkable happens. Hydrogen, normally a gas or a simple molecular solid, transforms into a metal. This is metallic hydrogen, a phase of matter that was only created in laboratories on Earth in the last decade, and even then only for brief moments under extreme pressure. Inside Jupiter, There's an entire shell of this stuff thousands of kilometers thick. In metallic hydrogen, the pressure is so great that the hydrogen molecules break apart, and the electrons are no longer bound to individual atoms. They become delocalized, like in a metal, and the protons arrange themselves in a crystal lattice. The theoretical calculations suggest this material could be extraordinarily strong, with a tensile strength possibly exceeding 100 gigapascals. Some estimates go much higher. The problem is we have no way to measure it directly. Metallic hydrogen only exists under pressures around 100 to 400 gigapascals, and if you release that pressure, it instantly decompresses. The few times we've created it on Earth, the samples either exploded or disappeared as soon as the pressure dropped. There's also no way to extract it from Jupiter. So, metallic hydrogen is strong, probably stronger than anything we can make on Earth, but it's trapped inside giant planets where we can't get to it. But at least it's still matter we can understand with chemistry. Now, let's talk about exotic ices. Water is weird. Most substances get denser when they freeze, but ice floats on water because the crystal structure of ordinary ice has a lot of empty space. That's ice I, the stuff in your freezer. But if you increase the pressure, water forms different kinds of ice with different crystal structures. Ice U2, Ice 3, Ice Vi, Ice Vi. These aren't just colder or denser versions of regular ice, they are distinct phases with different atomic arrangements. At extremely high pressures, you get Ice 7, where water molecules are packed so tightly that the hydrogen bonds barely matter anymore. Each oxygen is surrounded by 8 neighbors instead of 4. The density increases dramatically. Go even higher and you get Ice X, where the hydrogen atoms sit exactly halfway between oxygen atoms and the distinction between molecules starts to break down. And then there's superionic ice, a bizarre phase where the oxygen atoms lock into a crystal lattice, but the hydrogen atoms flow through it like a liquid. This exists in the cores of Uranus and Neptune, where pressures reach a few hundred gigapascals and temperatures hit a few thousand degrees. These exotic ices are stronger than regular ice, but they're still bound by chemistry. They're still playing by the same rules. And they suffer from the same problem as metallic hydrogen. They only exist under extreme conditions. Bring them to Earth's surface and they revert to ordinary ice or water or steam. The lesson here is that strength depends on context. A material that's incredibly strong at 500 gigapascals and 3,000 degrees might not even be stable at room temperature and atmospheric pressure. We are starting to see that the strongest materials in the universe are strong, precisely because they exist in environments that would annihilate everything else. Now, we need to take a bigger leap. We need to leave planets behind and visit something far more extreme. We need to visit a star that's died. When a star like the Sun runs out of fuel, it doesn't go out gently. For billions of years, it's been fusing hydrogen into helium in its core, and the energy from that fusion creates an outward pressure that balances the inward pull of gravity. But eventually, the hydrogen runs out. The core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. This buys some time, but not much. When the helium runs out, stars like the Sun don't have enough mass to fuse carbon. The fusion stops, and without that outward pressure, gravity wins. The core collapses. For a star like the Sun, this collapse creates what's known as a white dwarf. The outer layers get blown away in a planetary nebula, and what's left is the collapsed core. A white dwarf is roughly the size of Earth, but contains about half the mass of the Sun. That's an almost incomprehensible density. A teaspoon of white dwarf material would weigh about 5 tons, as much as an elephant. How is this possible? What's holding up the star against gravity now that fusion has stopped? The answer is electron degeneracy pressure. This is a quantum mechanical effect that arises from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. As the star collapses, the electrons get squeezed closer and closer together until they start resisting further compression, not because of electromagnetic forces, but because quantum mechanics forbids them from occupying the same space. It's not a force in the traditional sense. It's a pressure that emerges from the fundamental rules of quantum mechanics. And it's strong enough to hold up a star. The core of a white dwarf is mostly carbon and oxygen, the leftover products of helium fusion arranged in a crystalline lattice. But this isn't like any crystal you've ever seen. The pressure at the center of a white dwarf can reach 1 billion gigapascals, 10 million times greater than the pressure at Earth's core. Under these conditions, the carbon and oxygen atoms are packed together far more tightly than they ever could be on Earth. The lattice is incredibly rigid. The material is extraordinarily strong. But here's the thing. This is still matter made of atoms. The electrons are degenerate, meaning they're packed as tightly as quantum mechanics allows, but they're still electrons orbiting nuclei. The atoms are still discrete entities. We're still in the realm of what you might call normal matter. White dwarf matter represents the densest that normal matter can get before something fundamental breaks. Because if you add more mass, if you compress it further, electron degeneracy pressure eventually fails. And when it fails, something even more extreme happens. If a white dwarf accumulates too much mass, either by pulling material from a companion star or by colliding with another white dwarf, it can cross a threshold known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Beyond this point, electron degeneracy pressure can no longer support the star. Gravity overwhelms the quantum resistance of the electrons, and the star collapses again. But this time, the collapse doesn't stop at a white dwarf. This time, the electrons get forced into the protons, combining to form neutrons through a process called inverse beta decay. The star becomes a neutron star. And this is where things get truly incomprehensible. A neutron star is about 20 kilometers across, roughly the size of a city, but it contains 1 to 2 times the mass of the Sun. If a white dwarf has the density of an elephant per teaspoon, a neutron star has the density of Mount Everest per teaspoon. The pressure at the core of a neutron star can reach 1 quadrillion gigapascals or more. We're not talking about atoms anymore. We're talking about atomic nuclei packed together with barely any space between them, held up not by electron degeneracy, but by neutron degeneracy pressure and the strong nuclear force itself. We're talking about matter so dense that a single cubic centimeter contains as much mass as a mountain. And it's in the crust of these neutron stars, in the transition zone between the surface and the core, that we find the strongest material in the universe. But to understand what that material is and why it's so strong, we need to take a journey into the neutron star itself. We need to descend through layers of increasingly bizarre matter, through conditions so extreme that the physics is still not fully understood, until we reach a region where the atomic nuclei themselves are stretched and squished and deformed into shapes that sound more like pasta than physics. That's where we're going next. Imagine standing on the surface of a neutron star. Actually, you can't stand on it because you'd be dead before you got anywhere close, but let's pretend for a moment. The surface gravity is roughly 200 billion times stronger than Earth's gravity. If you weigh 70 kilograms on Earth, you'd weigh 14 trillion kilograms on a neutron star, about the same as 2,000 Great Pyramids of Giza. Your body would be instantly flattened into a layer of atoms less than a millionth of a millimeter thick. Any mountain on the surface can't be more than a few millimeters tall before its own weight crushes it flat. The escape velocity is about 1/3 the speed of light. Light itself gets bent by the gravity, allowing you to see more than half the star's surface at once because the light curves around it. This is what happens when you compress 1 to 2 solar masses into a sphere about 20 kilometers across. This is a neutron star, and it's the most extreme environment in the universe that isn't a black hole. These objects form when massive stars, at least 8 to 10 times heavier than the Sun, run out of fuel and collapse. The core implodes in less than a second, and the outer layers rebound off the incompressibly dense core, creating a supernova explosion visible across millions of light years. What's left behind is a ball of neutrons held up by neutron degeneracy pressure and the repulsive component of the strong nuclear force, the same force that holds atomic nuclei together. The density is beyond anything we can truly comprehend. A single teaspoon of neutron star material would weigh about 4 billion tons, roughly the same as Mount Everest. A thimbleful would outweigh all of humanity. If you could somehow bring a piece of neutron star to Earth, it would punch through the planet like it wasn't even there, and probably oscillate back and forth through the center until it settled at the core. Neutron stars spin rapidly, some completing hundreds of rotations per second. They have magnetic fields trillions of times stronger than Earth's, strong enough to erase the information on a credit card from halfway across the solar system and give you a lethal dose of radiation from thousands of kilometers away. The fastest known neutron star, designated PSRJ 1748-2-446 AD, rotates 716 times per second. The surface is moving at roughly 20% the speed of light. At that speed, the star is almost tearing itself apart, held together only by its own immense gravity. These are not friendly places. But here's what makes neutron stars truly special from a material science perspective. The conditions inside them create a natural laboratory for testing matter at extremes we could never reproduce on Earth. The pressure ranges from millions to quadrillions of times atmospheric pressure. The density goes from millions of times denser than water at the surface to densities that surpass that of atomic nuclei in the core. And in this environment, matter organizes itself into structures unlike anything else in the universe. Let's descend into a neutron star and see what we find. At the surface, things are almost normal. Almost. The atmosphere, if you can call it that, is only a few centimeters thick and composed of hydrogen or helium plasma at temperatures of around 1,000,000 degrees. Below that is the outer crust, starting at a density of about 1,000,000 grams per cubic centimeter. For comparison, lead has a density of about 11 grams per cubic centimeter. In the outer crust, matter still resembles what we think of as normal, just compressed. You have iron nuclei, specifically iron 56, the most stable nucleus, arranged in a crystal lattice. These nuclei are embedded in a sea of electrons that have been squeezed into a degenerate state. The electrons aren't bound to specific nuclei anymore. They flow freely through the lattice like a fluid. This is similar to what happens in a white dwarf, but much more extreme. As we go deeper, the pressure increases, and something strange starts to happen. At lower pressures, iron 56 is the most stable nucleus, but at higher pressures, nuclei with more neutrons become energetically favorable. This is because neutrons don't have electric charge, so they don't experience the electromagnetic repulsion that protons feel when packed together in a nucleus. At extreme densities, having extra neutrons actually makes a nucleus more stable. So, as we descend, the iron 56 nuclei get replaced by progressively more neutron-rich isotopes. Iron 58, iron 60, then even heavier elements like nickel and krypton with absurd neutron-to-proton ratios that would be completely unstable under normal conditions. We're finding nuclei that don't exist anywhere else in the universe. At a depth of about half a kilometer, we cross a threshold known as the neutron drip line. The density here is around 400 million grams per cubic centimeter, about 100 million times denser than rock. At this point, the nuclei have so many neutrons that they can't hold on to all of them. Neutrons start dripping out of the nuclei and forming a free neutron gas that permeates the space between nuclei. Now we have a bizarre hybrid state. There are still nuclei arranged in a lattice, but they're swimming in a sea of free neutrons and degenerate electrons. The neutrons aren't bound to anything. They just exist as a quantum fluid filling the gaps. And this fluid behaves strangely. At the densities in the inner crust, the free neutrons form what's called a superfluid. This is a quantum state where the fluid has exactly zero viscosity. It flows without friction. If you could somehow stir it, it would keep spinning forever. Superfluidity is related to superconductivity, and both arise from quantum effects becoming important on macroscopic scales. In normal fluids, friction comes from interactions between particles. But in a superfluid, the particles are locked into a collective quantum state that minimizes energy, and any perturbation costs energy. So the fluid flows without resistance. The neutron superfluid in the inner crust of a neutron star is thought to extend from the neutron drip line down to the base of the crust, which is at a depth of about 1 to 2 kilometers depending on the star's mass. The density at the base of the crust reaches about 500 billion grams per cubic centimeter. That's approaching the density of an atomic nucleus itself. At this point, the nuclei are packed so tightly that they're almost touching. And this is where we encounter nuclear pasta. Nuclear pasta is not a joke, although the name makes it sound like one. It's the term physicists use to describe the exotic structures that atomic nuclei form in the transition region between the inner crust and the core of a neutron star. At densities just below and just above the crust core boundary, nuclei can no longer maintain their usual spherical shapes. The immense pressure squashes them together, and they deform into a variety of bizarre geometries. At slightly lower densities, you get spherical nuclei, but they're so large and so close together that they start to look like balls of dough pressed against each other. Physicists call this phase gnocchi, after the Italian dumpling. As the density increases, the nuclei elongate into rods, all aligned in the same direction like strands of spaghetti. Increase the density further, and the rods merge into sheets, called lasagna. Go even denser, and the structure inverts. Instead of sheets of nuclear matter separated by gaps, you get gaps shaped like tubes running through a continuous nuclear medium. These are called inverse spaghetti, or sometimes tubular pasta. And at even higher densities, the tubes fragment into spherical bubbles of low-density matter embedded in a high-density nuclear medium, called inverse gnocchi, or Swiss cheese. Finally, at the highest densities, The bubbles disappear entirely, and you're left with uniform nuclear matter. You've reached the core. These structures form because of a competition between the strong nuclear force, which wants to hold nucleons together, and the electromagnetic repulsion between protons, which wants to push them apart. At the extreme densities in the inner crust, the usual spherical nucleus is no longer the lowest energy configuration. The system can lower its energy by deforming into rods or sheets, spreading out the protons to reduce their mutual repulsion while still keeping the neutrons close enough to benefit from the strong force. The result is nuclear pasta, and this pasta is strong. Absurdly strong. Simulations suggest that nuclear pasta could have a breaking strength of around 10 billion gigapascals. That's 10 billion times stronger than steel. To put that in perspective, if you had a cable made of nuclear pasta with a cross-sectional area the size of a coin, you could hang a weight equivalent to 10,000 Mount Everests from it before it would snap. Or, to use a more cosmic comparison, you could use a hair-thin strand of nuclear pasta to lift the entire Earth. The reason nuclear pasta is so strong comes down to the forces involved. In ordinary materials, strength comes from electromagnetic forces between atoms or ions. But in nuclear pasta, you're dealing with the strong nuclear force, which is, as the name suggests, much stronger. The strong force operates over very short ranges, but within those ranges, it's the most powerful force in nature. Nuclear pasta exists right at the edge of what the strong force can hold together against gravity. The nuclei are packed so tightly that they're essentially one giant nucleus, or at least structures that blur the line between individual nuclei and bulk nuclear matter. Breaking nuclear pasta means overcoming the strong force binding between thousands or millions of nucleons simultaneously. It's like trying to rip apart the nucleus of an atom, except scaled up to macroscopic sizes. The exact strength depends on the specific phase of pasta and the density, and there's still some uncertainty in the calculations because the physics at these densities is not fully understood. But every simulation agrees on one thing. Nuclear pasta is far and away the strongest material in the universe. Now, here's the problem. We've never touched nuclear pasta. We've never even seen it directly. Everything we know about it comes from computer simulations and theoretical calculations based on our understanding of nuclear physics. So how confident are we that it actually exists? Pretty confident, actually, for several reasons. First, the simulations are based on well-tested theories of the strong nuclear force. Quantum chromodynamics, or QCD, is the theory that describes how quarks and gluons interact to form protons and neutrons, and how those nucleons interact with each other. QCD has been tested extensively in particle accelerators and matches experimental results extremely well. When physicists run simulations of matter at neutron star densities using QCD-based models, nuclear pasta emerges naturally. It's not something they put in by hand, it's a prediction of the theory. Second, we have indirect, observational evidence from neutron stars themselves. Neutron stars occasionally experience glitches, sudden increases in their rotation rate. These glitches are thought to be caused by interactions between the superfluid in the inner crust and the solid crust above it. The superfluid can spin faster than the crust, and when they couple together, the crust suddenly speeds up. The details of these glitches depend on the properties of the crust, including its strength. Observations of glitches are consistent with a crust that includes nuclear pasta. We also observe starquakes, sudden fractures in the neutron star crust that release enormous amounts of energy. The energy released in these quakes depends on how much strain the crust can store before breaking, which depends on its strength. The observed energies are consistent with a crust made of material far stronger than anything that could be made from ordinary atomic matter. One of the most dramatic pieces of evidence came in 2017, when the LIGO and Virgo gravitational wave detectors observed two neutron stars colliding. This event, designated GWW 170817, was the first time we detected gravitational waves from anything other than merging black holes. And unlike black holes, neutron star mergers also produce light, so telescopes all over the world turned to observe the aftermath. The gravitational wave signal from the merger contained information about how the neutron stars deformed as they spiraled into each other. Neutron stars aren't rigid spheres. They're slightly squishy, and the amount of squishiness, quantified by something called the tidal deformability, depends on the equation of state of the matter inside them. By measuring the gravitational waves, physicists were able to constrain the equation of state and determine that neutron stars are stiffer than some models predicted. This stiffness is consistent with a crust that includes strong exotic matter like nuclear pasta. We've also learned from X-ray observations. Neutron stars are incredibly hot, with surface temperatures of around 1,000,000 degrees, and they emit X-rays. By studying the X-ray spectra and how X-rays are absorbed as they pass through the star's atmosphere, astronomers can infer properties of the surface and crust. NASA's NICER mission, the Neutron Star Interior Composition Explorer, has been particularly useful for this. NICER is an X-ray telescope mounted on the International Space Station, and it's designed specifically to study neutron stars. By precisely measuring the timing and energy of X-rays from pulsars, NICER can map out hotspots on the surface and determine the star's radius and mass with unprecedented precision. These measurements help constrain the equation of state and support models that include nuclear pasta in the crust. So, while we can't directly sample nuclear pasta, the evidence that it exists is strong. The theory predicts it, the simulations show it, and the observations are consistent with it. Unless our understanding of nuclear physics is fundamentally wrong, nuclear pasta is real. But what happens if you try to break it? Neutron stars may be the strongest objects in the universe, but they're not indestructible. Every so often, the crust of a neutron star fractures. These fractures are called starquakes, and they're terrifying. A starquake happens when the crust can no longer support the stress placed on it. Neutron stars spin down over time as they emit radiation and lose rotational energy. As the star spins down, its shape changes slightly. A spinning object bulges at the equator due to centrifugal force, and as the spin rate decreases, the bulge decreases. But the crust is solid, and it resists this change. Over time, stress builds up in the crust as the star's interior adjusts to the slower rotation while the crust lags behind. Eventually, the stress exceeds even the immense strength of nuclear pasta, and the crust cracks. When it does, the star suddenly shifts to a new equilibrium shape. The equatorial bulge decreases by a fraction of a millimeter, which doesn't sound like much. But remember, this is a star with a mass greater than the Sun. The energy released in a starquake can be enormous. A typical starquake releases around 10 to the 39 ergs of energy. For comparison, the magnitude 9.5 Chilean earthquake of 1960, the most powerful earthquake ever recorded, released about 10 to the 25 ergs. A starquake releases 100 trillion times more energy, and that energy is released in a fraction of a second. The entire star rings like a bell, oscillating at frequencies of hundreds or thousands of hertz. These oscillations generate powerful bursts of radiation, mostly in the form of X-rays and gamma rays that radiate out into space. If a neutron star experiencing a starquake happened to be pointed at Earth, we'd see a sudden spike in X-ray and gamma-ray flux, and we have seen these events. Some neutron stars, called magnetars, have magnetic fields even stronger than typical neutron stars, up to 1,000 times more intense. Magnetars are particularly prone to starquakes because the stress in their crust comes not only from spin down, but also from the evolution of their magnetic field. The magnetic field inside a magnetar is so strong that it exerts physical pressure on the crust. As the field evolves, twisting and reconfiguring itself, it can crack the crust, triggering a starquake. When this happens, the magnetic field lines snap and reconnect, releasing a colossal burst of energy. On December 27, 2004, astronomers detected a gamma-ray flare from a magnetar designated SGR 1806-20. This object is about 50,000 light-years away, on the other side of the galaxy. The flare lasted only a tenth of a second, but in that brief instant, it released more energy than the Sun emits in 250,000 years. The radiation was so intense that it ionized Earth's upper atmosphere and disrupted radio communications. For a moment, this magnetar, located halfway across the galaxy, was brighter in gamma rays than the full moon is in visible light. That flare was caused by a starquake, a fracture in the crust that allowed the magnetic field to reconfigure violently. The energy came from the snapping of magnetic field lines, but the fracture itself was a failure of the crust. Even nuclear pasta, the strongest material in the universe, has limits, and when it breaks, the consequences are spectacular. The fact that we observe starquakes tells us something important. Nuclear pasta may be 10 billion times stronger than steel, but it's still a material, and materials can break. Strength is not the same as invincibility. The crust of a neutron star exists in a state of constant tension, pulled by gravity, spun by rotation, and twisted by magnetic fields. Over time, stress accumulates, and eventually, something has to give. But here's the thing. Even when nuclear pasta fails, it fails in a way that releases more energy than all the earthquakes in human history combined. That's what makes it the strongest material. It doesn't break easily, and when it does, it goes out with a bang. Nuclear pasta is the strongest material we're reasonably confident exists in the universe. But is it the absolute limit? Could there be something even stronger lurking in conditions we haven't fully explored? To answer that question, we need to go deeper. We need to descend past the crust of a neutron star and into the core, where the density becomes so extreme that our understanding of physics starts to break down, where matter might undergo a phase transition into something that isn't quite atoms and isn't quite a soup of fundamental particles, but somewhere disturbingly in between. At the base of the neutron star crust, where nuclear pasta gives way to the core, the density reaches about 500 billion grams per cubic centimeter. That's roughly the density of an atomic nucleus. You've essentially compressed matter to the point where there's no empty space left between nuclei. They're all touching, forming a continuous medium of nuclear matter. But what happens if you keep compressing? In the core of the most massive neutron stars, densities might reach several times nuclear density. At these extremes, we're not entirely sure what happens. the physics becomes uncertain because we can't recreate these conditions in laboratories, and the theoretical calculations become incredibly complex. One possibility is that matter remains as a fluid of neutrons with a small admixture of protons and electrons, all held together by neutron degeneracy pressure and the strong nuclear force. This is the standard model of a neutron star core. But there's another possibility that's far more exotic. At sufficiently high densities, the neutrons themselves might break apart. Remember, neutrons aren't fundamental particles. They're made of quarks. Specifically, each neutron contains 2 down quarks and 1 up quark, bound together by the strong force. Under normal conditions, quarks are confined inside protons and neutrons. You can't pull a quark out of a proton because the strong force gets stronger with distance, not weaker. Try to separate 2 quarks, and you'll just create new quark-antiquark pairs from the energy you're putting in. This phenomenon is called quark confinement, and it's one of the fundamental features of quantum chromodynamics. But at extreme densities, something interesting might happen. When neutrons are packed so tightly that they're overlapping, the distinction between individual neutrons starts to blur. The quarks that make up one neutron can interact with quarks from neighboring neutrons. At a critical density, it might become energetically favorable for the quarks to stop being organized into discrete neutrons and instead form a continuous fluid of deconfined quarks. This is quark matter. In quark matter, you no longer have neutrons or protons. You have a plasma of up quarks, down quarks, and electrons, all swimming around freely. The quarks are still held together by the strong force, but they're not confined to individual baryons anymore. They're in a state called quark-gluon plasma, similar to what existed in the first microseconds after the Big Bang when the universe was hot and dense enough that quarks couldn't form stable protons and neutrons yet. But here's where it gets even stranger. There's a third type of quark we haven't talked about yet. In addition to up and down quarks, there are also strange quarks. Strange quarks are more massive than up and down quarks, so under normal conditions, they're not stable. If you create a strange quark, it quickly decays into an up or down quark. But at the densities in a neutron star core, strange quarks might actually be stable. In fact, they might be more stable than having only up and down quarks. This is because of a principle in quantum mechanics related to the Pauli exclusion principle. Quarks, like electrons, are fermions, and they obey Fermi-Dirac statistics. What this means is that quarks of the same type can't all occupy the same low-energy states. As you pack more and more quarks together, they're forced to occupy higher and higher energy states. But strange quarks are a different type of quark. They have a different flavor quantum number. So, if you have a system that's densely packed with up and down quarks, you can lower the total energy by converting some of those quarks into strange quarks. The strange quarks can occupy low-energy states that are already filled by up and down quarks. The result is strange quark matter, a plasma composed of roughly equal numbers of up, down, and strange quarks in equilibrium. And here's the disturbing part. Some physicists have hypothesized that strange quark matter might be the true ground state of matter. What this means is that strange quark matter might be more stable than ordinary atomic matter. Everything around us, every atom in our bodies, every planet and star, might actually be in a metastable state. We might exist only because we haven't been exposed to strange matter yet. This idea is called the strange matter hypothesis, and it was first proposed by physicists Arnold Bodmer and Edward Witten in the 1970s and 80s. If the strange matter hypothesis is true, then a sufficiently large lump of strange matter would be absolutely stable. It wouldn't decay. And, more alarmingly, if strange matter came into contact with ordinary matter, it might convert it. The strange quarks would be at a lower energy state than the up and down quarks in normal atomic nuclei, so the nuclei would spontaneously disassemble and rearrange themselves into strange quark matter. And, once the conversion starts, it would be autocatalytic. The newly created strange matter would convert more ordinary matter, which would create more strange matter, and so on. The conversion would propagate through any ordinary matter it touched at nearly the speed of light, converting everything in its path into a growing blob of strange quark matter. This is sometimes called the Ice-9 scenario, after a fictional substance in Kurt Vonnegut's novel Cat's Cradle. In the book, Ice-9 is a polymorph of water that's more stable than regular ice, and when it touches liquid water, it causes the water to instantly freeze into more Ice-9, with catastrophic consequences. Strange matter would work the same way. If a chunk of strange matter the size of a grain of sand hit Earth, it would tunnel through the planet, converting everything it touched into strange matter. Within hours or days, the entire Earth would be converted into a hot, dense sphere of strange quark matter, about 100 meters across. You, me, everyone you've ever known, every mountain and ocean, every bit of the biosphere, all converted into an exotic plasma of quarks. It's a terrifying idea, but before you panic, there are good reasons to think this probably won't happen. First, the strange matter hypothesis might just be wrong. Whether strange matter is actually more stable than ordinary matter depends on the precise details of the strong force and how quarks interact at high densities, and we don't know those details well enough to say for certain. Most calculations suggest that strange matter is not the true ground state, or if it is, the energy difference is so small that the conversion wouldn't happen easily. Second, even if strange matter is more stable, it might not be able to convert ordinary matter in practice. The conversion would require overcoming an energy barrier. Atomic nuclei are held together by the strong force, and you'd need to input energy to break them apart before they could rearrange into strange matter. At the densities and temperatures inside a neutron star, this might happen, but at the low densities and temperatures of normal matter, the barrier might be too high. Third, if strange matter were really this dangerous and really this common, we'd probably already be gone. Cosmic rays bombard Earth all the time with particles at incredibly high energies, including heavy nuclei traveling at nearly the speed of light. Some of these collisions create conditions similar to those in the early universe or the interior of neutron stars, at least for tiny fractions of a second. If those collisions could create stable strange matter, and if that strange matter could convert ordinary matter, it would have happened already. The fact that Earth still exists is decent evidence that strange matter either doesn't exist, isn't stable, or isn't contagious. But let's entertain the possibility that strange matter does exist, at least in the cores of neutron stars. If a neutron star's core is dense enough, the center might undergo a phase transition from normal nuclear matter to strange quark matter. The star would then have a strange quark core surrounded by a crust of nuclear pasta and normal nuclear matter. Some physicists even speculate that there might be objects called strange stars or quark stars that are entirely made of strange matter with no normal crust at all. a strange star would be even denser than a neutron star. For the same mass, a strange star would be smaller, perhaps only 10 kilometers in diameter instead of 20. The density at the surface would be even higher, and the gravity even more intense. And if strange matter really is more stable than normal matter, a strange star would be the ultimate endpoint of stellar collapse, the most stable, lowest energy configuration for a given amount of baryonic matter. Now, here's the question. Would strange matter be stronger than nuclear pasta? It's hard to say because we don't know the properties of strange matter well enough, but there are reasons to think it might be. Nuclear pasta is strong because it's held together by the strong force at nuclear densities. Strange matter is also held together by the strong force, but at even higher densities. The quarks in strange matter are packed more tightly than the nucleons in nuclear pasta. And because the strong force gets stronger at short distances, the binding might be even tighter. On the other hand, strange matter is a fluid, not a solid. It doesn't have a crystal structure like nuclear pasta does. Fluids can resist compression, but they can't resist shear stress. You can't pull on a fluid the way you can pull on a solid. So, in terms of tensile strength, strange matter might actually be weaker than nuclear pasta, even though it's denser and more tightly bound. But here's another possibility. At the very center of the most massive neutron stars, where densities are highest, quark matter might not be a simple fluid. It might undergo another phase transition into something even weirder. Something called color superconductivity. To understand color superconductivity, we need to take a quick detour into the quantum properties of quarks. Quarks carry a property called color charge. This has nothing to do with actual colors. It's just a name for a quantum number that comes in 3 types: red, green, and blue. The strong force is mediated by particles called gluons, and gluons interact with color charge the same way photons interact with electric charge. In normal matter, quarks are always confined in groups where the total color charge is neutral. A proton contains 1 red quark, 1 green quark, and 1 blue quark, which adds up to colorless. But in quark matter, where quarks are deconfined, they can have individual color charges. At sufficiently high densities and low temperatures, something remarkable can happen. Quarks of different colors can pair up, forming bound states similar to Cooper pairs in superconductors. In a normal superconductor, electrons with opposite spins pair up, and the pairs condense into a quantum state that allows electric current to flow without resistance. In a color superconductor, quarks with different color charges pair up, and the pairs form a condensate that has unusual properties. One of the most interesting phases is called the color flavor locked phase, or CFL phase. In this state, quarks pair up in such a way that all 9 combinations of color and flavor form Cooper pairs. The result is a state where the distinction between different colors and flavors is blurred, and the system is locked into a highly symmetric configuration. The CFL phase is predicted to be incredibly robust. It has an energy gap, meaning it takes a certain amount of energy to excite the system out of the superconducting state. This gap could be as high as 100 megaelectron volts, which is enormous by the standards of condensed matter physics. The CFL phase would be a superconductor for the strong force, and it would have vanishingly small viscosity, similar to a superfluid. But here's the key point. The CFL phase might also be incredibly stiff. The pairing of quarks creates a collective structure that resists deformation. Some theoretical calculations suggest that the shear modulus of the CFL phase, a measure of resistance to shear stress, could be even higher than that of nuclear pasta. If that's true, then the CFL phase might be the strongest form of matter in the universe. But, and this is a big, but we have no direct evidence that the CFL phase actually exists. It's a prediction of quantum chromodynamics at finite density, but the calculations are extremely difficult. The theory of QCD is well tested at low densities and high energies, like in particle colliders, but at the high densities and moderate energies inside neutron stars, the calculations require approximations that might not be valid. We're in a regime where theory is ahead of experiment, and we're not sure which theoretical predictions to trust. So, do strange stars exist? Are there neutron stars with cores made of quark matter or strange matter or color superconducting matter? The honest answer is we don't know. But there are some intriguing hints. Astronomers have found a few neutron stars that seem anomalous. They're either too small, too dense, or too cold compared to standard neutron star models. One of the most famous candidates is RxJ 185.6.5-3754, a nearby neutron star that's only a few hundred light-years away. Observations suggest it has a radius of only about 10 to 12 kilometers, smaller than most neutron star models predict. A smaller radius for a given mass implies a higher density, which could indicate the presence of exotic matter in the core. Another candidate is PSR J0348+0432, a pulsar with an unusually high mass of about 2 solar masses. Neutron star models have a hard time explaining how a star that massive can be supported by normal nuclear matter without collapsing into a black hole. Some models suggest that a quark matter core could provide the additional pressure needed to stabilize such a massive star. There's also PSR J 0740+6620, another massive pulsar with a mass around 2 solar masses. Its radius is difficult to measure, but some estimates suggest it might be smaller than expected. These are all tantalizing hints, but they're not conclusive. The problem is that measuring the size of a neutron star is incredibly difficult. Neutron stars are tiny, only about 20 kilometers across, and they're far away, typically hundreds or thousands of light-years. We can't resolve them with telescopes. Instead, we have to infer their size from indirect measurements. One method is to observe X-rays from hotspots on the surface. As the neutron star rotates, the hotspots move in and out of view, causing the X-ray brightness to oscillate. By analyzing the pattern of these oscillations and how the light is bent by the star's gravity, we can infer the star's radius. This is what NASA's NICER mission has been doing. In 2019, NICER released measurements of the radius of PSR J0030+0451, a pulsar about 1,000 light-years away. The result was a radius of about 12 to 13 kilometers, which is consistent with standard neutron star models but doesn't rule out exotic matter. The uncertainty in the measurement is still large enough that a quark matter core is possible. Gravitational waves might provide more definitive answers. When two neutron stars merge, the gravitational waves they emit carry information about their internal structure. The way the stars deform as they spiral together depends on the equation of state, the relationship between pressure and density inside the star. By detecting more neutron star mergers and analyzing the gravitational wave signals, we can constrain the equation of state and potentially detect signatures of exotic matter. The 2ATUAU 1017 neutron star merger, GW170817, provided the first such constraints, but the uncertainty is still large. we need more events to narrow it down. Another approach is to look for strange stars directly. If strange stars exist and are made entirely of strange matter, they might have different observable properties. For example, the surface of a strange star might be bare quark matter instead of a crust of atomic nuclei. This could affect the star's temperature, its spectrum, and how it cools over time. Some astronomers have searched for objects with anomalous cooling rates or unusual spectra that might indicate a bare strange matter surface. So far, no definitive strange stars have been found, but the search continues. There's also the disturbing possibility that we could create strange matter in particle colliders. When heavy ions like gold nuclei are smashed together at nearly the speed of light, the collision creates a tiny, short-lived region of extremely high energy density. For a brief moment, conditions resemble those in the early universe or the core of a neutron star. Quarks are liberated from protons and neutrons, forming a quark-gluon plasma. Experiments at the relativistic Heavy Ion Collider in the United States and the Large Hadron Collider in Europe have created and studied this quark-gluon plasma. But could these collisions create strange matter? And if they did, would it be stable? Physicists have thought carefully about this, and the consensus is no. The conditions in a collider are extreme but short-lived. The quark-gluon plasma exists for only about 10 to the minus 23 seconds before it expands and cools, and the quarks recombine into normal protons and neutrons. There's no time for strange matter to form, and even if it did, the tiny droplet would be so hot and so small that it would evaporate or decay almost instantly. But the fact that physicists took this seriously enough to study it tells you something. Strange matter, if it exists, is strange in more ways than one. So where does this leave us? Nuclear pasta is the strongest material we're confident exists. It's held together by the strong nuclear force at densities approaching that of atomic nuclei, and it can withstand stresses 10 billion times greater than steel. But deeper in the cores of neutron stars, where densities exceed nuclear density, matter might undergo a phase transition into quark matter, strange matter, or even more exotic phases like the color-flavor locked state. These phases might be even stronger than nuclear pasta, or they might not. We don't know. The physics at these densities is still uncertain, and we have no way to directly observe or measure the properties of matter in neutron star cores. What we do know is that neutron stars are the ultimate laboratory for studying matter under extreme conditions. Every observation, every gravitational wave detection, every X-ray pulse brings us closer to understanding what happens at the boundary of our physical theories. And somewhere in the cores of the most massive neutron stars, at densities we can barely imagine, matter exists in forms that might be the strongest, the strangest, and the most exotic in the universe. We started this journey with a simple question. What is the strongest material in the universe? We began with diamond, a crystal of carbon atoms locked in a rigid lattice, the hardest substance on Earth. Then we moved to graphene, a single sheet of carbon with theoretical strength 200 times greater than steel. But these materials, impressive as they are bound by the limits of chemistry. The electromagnetic force between atoms can only be so strong, and you can only pack atoms so close together before their electron clouds repel each other. So we left Earth behind and ventured into space, where gravity compresses matter to densities unimaginable on our planet. We found exotic ices in the cores of giant planets, metallic hydrogen squeezed into existence by pressures that would vaporize any spacecraft we could build. we descended into white dwarfs, where electron degeneracy pressure holds up a star's worth of mass in a sphere the size of Earth, creating crystals of carbon and oxygen at densities where a teaspoon weighs as much as an elephant. And then we went deeper still into neutron stars, where gravity is so strong that atoms collapse entirely, where electrons are forced into protons, creating a sea of neutrons packed together at nuclear density, where the crust is made of nuclei with impossible neutron-to-proton ratios, swimming in a superfluid of free neutrons. And in the transition zone between the crust and the core, we found nuclear pasta, a bizarre collection of structures where atomic nuclei are squished into rods and sheets and bubbles, held together by the strong nuclear force itself. Nuclear pasta is 10 billion times stronger than steel. It can withstand forces that would shatter every other material in the universe. But is it the absolute limit? To answer that, we need to ask a more fundamental question. What determines the ultimate limit of material strength? At its core, the strength of any material comes down to the forces holding it together. In ordinary matter, that's the electromagnetic force acting between charged particles. In nuclear pasta, it's the strong nuclear force acting between quarks and gluons inside nucleons. The strong force is, as the name suggests, the strongest of the fundamental forces. But it operates over incredibly short ranges, only about 1 femtometer, roughly the size of a proton. As long as particles are within that range, the strong force can bind them together with incredible strength. But there's a limit to how tightly you can pack matter, even with the strong force. At some point, you run into the fundamental graininess of space-time itself. This is where we enter the realm of Planck scale physics, named after Max Planck, one of the founders of quantum mechanics. The Planck length is about 10 to the minus 35 meters, many orders of magnitude smaller than a proton. It's the scale at which quantum effects of gravity become important, where space-time itself might be quantized, breaking down into discrete units rather than being a smooth continuum. If you try to probe distances smaller than the Planck length, quantum fluctuations in space-time become so large that the very notion of distance stops making sense. At the Planck scale, all 4 fundamental forces, gravity, electromagnetism, the strong force, and the weak force, become comparable in strength. Our current theories of physics break down because we don't have a consistent theory of quantum gravity. General relativity, which describes gravity, and quantum mechanics, which describes the other forces, are incompatible at these scales. So what happens to matter at the Planck scale? We don't know. We can speculate, but we're beyond the reach of both experiment and well-tested theory. Some physicists have hypothesized the existence of Planck matter, a state of matter at densities around 10 to the 96 kilograms per cubic meter. For comparison, nuclear pasta has a density of around 10 to the 18 kilograms per cubic meter. Planck matter would be almost 80 orders of magnitude denser. At those densities, space and time themselves might be part of the material structure. You wouldn't have particles in space-time. You'd have space-time made of some more fundamental quantum entities, whatever those might be. But here's the problem. We have no idea if Planck matter can actually exist, and if it does, the only place it might exist is inside black holes. When you compress matter beyond the point where even the strong nuclear force can resist gravity, you get a black hole. The transition happens when you squeeze enough mass into a small enough volume that the escape velocity exceeds the speed of light. At that point, not even light can escape. You've created an event horizon, a one-way boundary in space-time. Once something crosses the event horizon, it can never come back out. This is what happens to nuclear pasta if you compress it further. Add more mass to a neutron star, and eventually you reach a limit, somewhere between 2 and 3 solar masses depending on the equation of state. Beyond this limit, neutron degeneracy pressure fails. The strong force fails. Nothing can hold up the star against gravity. The star collapses into a black hole. And then things get weird. Inside the event horizon, our understanding of physics becomes speculative. General relativity predicts that all the matter collapses toward a singularity, a point of infinite density at the center of the black hole. But infinity is usually a sign that your theory is broken. Most physicists don't believe the singularity is real. They think it's a placeholder for something we don't yet understand, something that requires a theory of quantum gravity to describe properly. So, does matter still exist inside a black hole? Does it make sense to talk about the strength of materials inside the event horizon? Maybe not. Once you're inside a black hole, time and space swap roles in a certain mathematical sense. The singularity isn't a place in space. It's a moment in your future, as inevitable as next Thursday. You can't avoid it any more than you can avoid tomorrow. And as you fall toward the singularity, tidal forces stretch you along the direction of motion and compress you perpendicular to it, a process charmingly called spaghettification. For a large black hole, you might survive crossing the event horizon because the tidal forces are initially weak. But as you get closer to the singularity, the forces grow without bound. Eventually, they exceed any possible material strength. Your atoms are ripped apart. Then the nuclei are ripped apart. Then the quarks are ripped apart. And then, well, we don't know. Maybe space-time itself is ripped apart. The point is, black holes might not contain the strongest material in the universe. They might not contain material at all, at least not in any sense we would recognize. The singularity might be a quantum foam of space-time, a region where the concept of matter breaks down entirely. Or it might be something else. Something we'll need a theory of quantum gravity to understand. So nuclear pasta remains the strongest material we can meaningfully talk about. But here's a frustrating fact. We can never use it. Even if we could somehow extract a chunk of nuclear pasta from a neutron star, which we can't, it wouldn't stay nuclear pasta for long. Nuclear pasta only exists at densities around 500 billion grams per cubic centimeter, sustained by the immense gravity of the neutron star. Remove it from that environment, and it would explosively decompress. The pressure holding it together would vanish, and the material would expand violently, probably vaporizing into a cloud of neutrons and protons and releasing an enormous amount of energy in the process. You couldn't hold it. You couldn't store it. You couldn't build anything with it. It would be gone before you could blink. The same is true for all the exotic materials we've discussed. Metallic hydrogen, exotic ices, white dwarf matter, strange matter. They all require extreme conditions to remain stable. Bring them to ordinary pressures and temperatures and they revert to normal matter, or simply explode. So, can we at least recreate these conditions on Earth? Can we build a device that generates the pressures inside a neutron star? Not really, no. The highest pressures we can achieve in laboratories are impressive, but nowhere near sufficient. Diamond anvil cells, which squeeze tiny samples between 2 diamonds, can reach pressures of a few hundred gigapascals, comparable to the center of the Earth. That's enough to study exotic ices and maybe metallic hydrogen for brief moments, but it's 1,000,000 times too weak to create nuclear pasta. Particle colliders can do better, but only for incredibly short times. When heavy ions collide at the relativistic Heavy Ion Collider in New York, or the Large Hadron Collider in Switzerland, they create a fireball of quark-gluon plasma, a state of matter similar to what exists in the cores of neutron stars. For a brief moment, about 10 to the minus 23 seconds, the temperature and density in the collision region are high enough that quarks are liberated from protons and neutrons. But the fireball is tiny, only about 10 femtometers across, roughly the size of a large nucleus, and it expands and cools almost instantly. There's no time for stable structures to form. The quark-gluon plasma expands, the quarks recombine into protons and neutrons, and you're left with a spray of ordinary particles. You've touched the conditions inside a neutron star for less than the time it takes light to cross an atom. Another approach is the National Ignition Facility in California, where scientists use powerful lasers to compress and heat tiny pellets of hydrogen isotopes. The goal is to achieve nuclear fusion, the same process that powers the sun. At the moment of peak compression, the pressures in the fuel can briefly reach a few 100 billion atmospheres, approaching the pressures in the outer layers of a white dwarf. But again, this lasts only for nanoseconds before the fuel explodes outward. So we can touch these extreme states for a fraction of a second, but we can't sustain them. We can create conditions similar to the cores of stars, but we can't build anything out of the materials that exist there. Even if we could somehow stabilize nuclear pasta at room temperature and atmospheric pressure, which we can't, it's not clear what we'd use it for. A material 10 billion times stronger than steel sounds useful until you realize you have no way to shape it, no way to machine it, no way to connect it to anything else. How do you drill a hole in something that's stronger than any drill bit could ever be? How do you weld two pieces together when no torch could possibly melt it? The strongest material in the universe is also the least practical. But that doesn't mean these materials are useless to us. Even though we can't use them to build spacecraft or bridges, studying them teaches us fundamental things about the universe. The hierarchy of material strength, from chemical bonds to nuclear forces to exotic quark matter, mirrors the hierarchy of the fundamental forces of nature. Each step up in density and strength corresponds to probing a different layer of physical reality. By understanding how matter behaves at neutron star densities, we learn about the strong nuclear force, the least understood of the fundamental interactions. By studying nuclear pasta and quark matter, we test the predictions of quantum chromodynamics, the theory of quarks and gluons. These aren't just abstract exercises. The same physics that governs neutron stars also governed the early universe. In the first microseconds after the Big Bang, the entire universe was hot and dense enough that quarks were deconfined, forming a cosmic soup of quark-gluon plasma. As the universe expanded and cooled, quarks combined into protons and neutrons, and then protons and neutrons combined into the first atomic nuclei. This process, called Big Bang nucleosynthesis, determined the initial abundances of hydrogen, helium, and lithium in the universe, the raw materials from which all later structure would form. By studying neutron stars, we're studying a snapshot of the early universe, frozen in time. Neutron stars are laboratories where we can observe matter under conditions that otherwise existed only in the first moments of creation. And, because neutron stars are relatively nearby and long-lived, we can study them in detail, measuring their masses and radii and observing how they behave when they collide. Every observation of a neutron star is a test of our theories of nuclear physics and quantum chromodynamics. Every gravitational wave from a neutron star merger tells us something about the equation of state of dense matter. Every X-ray pulse, every glitch, every starquake is a data point that helps us understand the fundamental forces. There's also a beautiful irony in the fact that the strongest materials in the universe exist in the most violent places. Neutron stars are born in supernova explosions, some of the most energetic events in the cosmos. They spin hundreds of times per second, emit beams of radiation that sweep across the galaxy, and occasionally crack their own crust in starquakes that release more energy than all the earthquakes in human history. The very conditions that create the strongest materials are the same conditions that would annihilate any life or civilization trying to study them up close. And that brings us back to the beginning. We asked what the strongest material in the universe is, and the answer is nuclear pasta, a bizarre form of matter that exists only in the crust of neutron stars, held together by the strong nuclear force at densities where atoms cease to exist. It's 10 billion times stronger than steel. You could hang 10,000 Mount Everests from a cable the size of a coin before it would break. But you can't touch it. You can't use it. If you brought it to Earth, it would explode. It exists only in the most extreme environments, places where the temperature is 1,000,000 degrees and the gravity is so strong that a fall of 1 millimeter would accelerate you to a significant fraction of the speed of light. In other words, the strongest material in the universe is completely inaccessible. And maybe that's for the best. Because the flip side of strength is fragility. Diamond is hard, but it shatters. Steel is strong, but it bends. Nuclear pasta can withstand forces that would vaporize any other material, but it exists in a universe that constantly tries to destroy it. Gravity pulls it inward. Rotation tries to tear it apart. Magnetic fields twist it until it cracks, and when it breaks, the energy released is apocalyptic. Meanwhile, here on Earth, we build our civilization out of materials that are weak by cosmic standards. Steel, concrete, silicon, carbon fiber. These materials aren't the strongest, but they're stable. They exist at the temperatures and pressures where life can exist. They can be shaped and worked and combined. We can hold them in our hands. And that weakness, that fragility, is what allows complexity to exist. If the world were made of nuclear pasta, there would be no chemistry, no molecules, no life. The electromagnetic force, the weakest of the forces governing matter, is the one that allows atoms to bond in the intricate patterns that make up DNA and proteins and everything else that makes life possible. Strength, in the cosmic sense, is incompatible with complexity. The strongest materials in the universe are also the simplest. Nuclear pasta is just neutrons and protons squished together. Quark matter is just quarks. The closer you get to the fundamental forces, the stronger the material, but the less interesting it becomes from the perspective of information and structure. Life, intelligence, civilization, all of it depends on weakness. On forces that are just strong enough to hold molecules together, but weak enough to allow them to change and interact and evolve. We exist in the narrow band of conditions where matter is neither too strong nor too weak, where the electromagnetic force dominates but doesn't overwhelm, where complexity can flourish. So maybe the question we should have asked isn't what's the strongest material, but what's the most useful material? And the answer to that would be something much more mundane. Water, perhaps, or carbon, or silicon. Materials that don't shatter mountains but do allow life to exist. The universe is full of extremes. The hottest, the coldest, the densest, the fastest, the strongest. And humans, being curious creatures, are drawn to these extremes. We want to know what's out there, what's possible, what happens at the edge of physical law. But we should also be grateful that we live in the middle, in the boring part of the universe where stars shine steadily and planets orbit predictably. And matter is just weak enough to be interesting. Nuclear pasta is the strongest material in the universe, but you're made of something far more remarkable. You're made of molecules that can store information, that can replicate, that can evolve. You're made of atoms that can bond and unbond, that can form the proteins and lipids and nucleic acids that make life possible. And those atoms exist in a narrow range of temperatures and pressures where the forces balance just right. Too much stronger, and you'd be a lump of inert matter. Too much weaker, and you'd dissipate into a cloud. So, yes, nuclear pasta is stronger than anything on Earth. It's stronger than diamond, stronger than steel, stronger than anything we could ever build. It exists in neutron stars, objects so extreme that they border on the incomprehensible. And if you ever find yourself on the surface of a neutron star, about to test the strength of nuclear pasta firsthand, well, you'll have exactly 0 time to appreciate it before you're flattened into a layer of atoms and incorporated into the crust. But here on Earth, in our fragile bubble of habitability, we can look up at the stars and wonder. We can observe neutron stars from a safe distance, study their glitches and their starquakes, listen to the gravitational waves from their collisions. We can use mathematics and physics to probe the properties of matter under conditions we'll never experience. We can ask what's the strongest, what's the hottest, what's the densest, and then we can be thankful that we're not there. Because the strongest material in the universe exists in the most hostile places. And the fact that we can study it from here, from our comfortable planet with our weak materials and our fragile bodies, is a testament to the power of curiosity and intelligence. We asked, what's the strongest material in the universe? And we found the answer. It's nuclear pasta, a form of matter so extreme it sounds like science fiction. But maybe the better question is this: what allows us to even ask the question in the first place? And the answer to that is the weakness that lets us exist, the delicate balance of forces that makes complexity possible, the narrow band of conditions where life can emerge and wonder about the universe. The strongest material in the universe is out there, in the cores of dead stars, holding together under forces that would annihilate everything we know. And that's exactly where it should stay.